Standard temperature and pressure, or STP. That's when the pressure is 1 atm and the temperature is 0 degrees Celsius. Only at those two conditions can you use the fact that the molar volume of an ideal gas is 22.4 liters. So only when you see these two conditions can you say that 1 mole is equal to 22.4 liters. So don't try and use this all the time. It only works a small percentage of the time. Alright, so for example, what is the mass of helium required to fill a 1.5 liter balloon at STP? Because we see STP, we know that 1 mole is equal to 22.4 liters. By the way, that's not given to you in your reference table, so you'll have to remember it. So 1.5 liters of helium. There's 22.4 liters of helium for 1 mole of helium. And 1 mole of helium is 4 grams of helium. That's the molar mass. So my liters cancel, moles cancel, and I'm left with grams. So that gives me 0.27 grams of helium. Now you can Pivnert this because you have your volume, and then STP, you should know if the temperature is 0 Celsius or 273 Kelvin and the pressure is 1 atm. So if you forget 1 mole is equal to 22.4 liters, you could just use the ideal gas law. In our second example, consider the following unbalanced chemical equation. So it's telling us that it's unbalanced, so we'll need to balance it. 6 carbons, 1 carbon, 12 hydrogens, 2 hydrogens. That gives me 6 oxygens here to balance my 6 oxygens. And then I have 6 times 2, so I don't need to put a 6 there. So it's 1666. What volume of oxygen gas measures at 28 degrees Celsius and 0.976 atm is needed to react with 5 grams of C6H12O6. Now notice that that is a solid. Because that's a solid, I can't use Pivnert with that value. I'm going to have to convert it to a gas before I can use any of my gas laws. So we'll set up a little conversion here. Molar mass is 180. And then we can use the mole ratio. So when we multiply and divide, we get 0.167 moles of oxygen. Now notice that we're at 28 degrees Celsius and 0.976 atm. So we're not at standard temperature and pressure. So we can't use the 22.4. So we have to use Pivnert. So the volume then is going to be our moles times our R constant, and I'm going to use 0.0821 liter atm over mole Kelvin. 28 degrees Celsius plus 273 is 301 Kelvin, divided by 0.976 atm. You really do want to use your units to make sure that you have all of your conversions right. So that would leave us with atm. I'm sorry, that leaves us with liter. 4.23 liters of O2. What volume of each product is produced under the same conditions? So then, since they're at the same temperature and pressure, we can look at their coefficients to see the ratios. Since they all have the same coefficients, oxygen, carbon dioxide, and water, they will all have the same volume. And that's Avogadro's law. Dalton's law of partial pressure. So among the experiments that led John Dalton to propose the atomic theory were his studies on mixtures of gases. In 1803, Dalton found for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it was alone. So we say that the total pressure is equal to the sum of the individual pressures. The partial pressure of each gas in a mixture depends on the total number of moles. So for example, we have 4 blue, 10 red. So when we come in here, the 4 blue is going to change how we look at it versus the 10 red. So moles do play somewhat of a role here. So we can take Dalton's law and say that the pressure of a gas is equal to the total pressure times the mole fraction of the gas. And a mole fraction is just the moles of the gas over the total moles. So if we were looking at the blue gas, we'll do B for blue, it would be 4 over 14 because I have 4 blue, but my total is 14. If I was looking at the red, we'll use R, 10 over 14. So if I know the total pressure and I know the mole fraction, I can actually solve for the individual pressure of that gas. For a mixture of ideal gases, it is the total number of moles of the particle that is important, not the identity or composition of the gas particles. So the volume of the individual gas particles must not be important. The forces among the particles must also not be important. So what we're saying is that the volume that the gas molecule actually takes up is nothing compared to the space between the molecules, and that there's no forces acting on them. So the gas particles aren't attracted to each other, but they don't repel each other either. So there are no IMFs, no intermolecular forces. Now that's for an ideal gas. Remember that we're only considering ideal gases right now. We'll talk about real gases at the end. So for example, a piece of solid carbon dioxide with a mass of 7.8 grams is placed into a 4-liter, otherwise empty container at 27 degrees Celsius. So let's go ahead and convert that to 300 Kelvin. What is the pressure in the container after all the carbon dioxide evaporates? If 7.8 grams solid carbon dioxide were placed in the same container, but it already contained an air of at 740 torr, what would be the partial pressure of the carbon dioxide and the total pressure of the container after the carbon dioxide evaporates? So there's a lot of stuff going on. First, convert to Kelvin. Second, I would go ahead and take my torr and convert it to ATM. So torr divided by 760 gives us 0.97 ATM. So I'm going to take my 7.8 grams, because I can't really do anything in grams, of carbon dioxide, and I'm going to convert it to moles. So 44 grams, 1 mole. That gives us 0.18 moles of carbon dioxide. Because I'm not at STP, because I'm looking for pressure, because I know volume and temperature, I'm going to use PIVNERT to solve for the pressure of CO2. And I'm going to put CO2 down there because I'm using information about CO2. So I'm going to check my units and make sure everything cancels out. Mole, mole, liter, liter, Kelvin, Kelvin. So I'm stuck with ATM. So that would give us 1.1 ATM. And that's for CO2. So that answers the first question. The second part of the question, the total pressure in the vessel once we have some already air in there. We're going to have the pressure of air plus the pressure of CO2. So I went ahead and converted it to ATM because I knew my answer for the pressure of carbon dioxide was in ATM. So do make sure that your units always match. So the pressure was 0.97 ATM plus the pressure of carbon dioxide. So my total pressure now is 2.1 ATM. Now if you wanted to leave it in torr, then you would have to make sure that you either use the R value that contained torr or converted your ATM to torr. If you did that, you would have gotten 1,596 torr. ATM is typically the better unit simply because it's a smaller value. Alright, the partial pressure of CH4 is 0.175 ATM and that of oxygen is 0.250 ATM. What is the mole fraction of each of the gases in the mixture? In order to figure that out, we need to know what the total pressure is. So the total pressure is going to be the sum of those two gases. So 0.175 ATM plus 0.250 ATM. Again, they're in the same units, we didn't need to convert. And we get 0.425 ATM. So the mole fraction then for CH4, I'm going to take the pressure of CH4, the total pressure, and that will give me the mole fraction of CH4. So the pressure was 0.175 ATM. That equals 0.425 ATM times the mole fraction. So solve for the mole fraction. And it is 0.412. I'm going to do the same thing for the oxygen. And we get 0.588. If the mixture occupies a volume of 10.5 liters at 65 degrees Celsius, calculate the total number of moles in the gas in the mixture. So here we're looking for total number of moles. So I want to use my total pressure. And then we're just going to pivot it. We have our volume and we have our temperature. Change that to Kelvin and it's 338 Kelvin. So my total, that's thinking something else. The total number of moles, and I'm going to say N total, is going to be equal to our pressure, total pressure, times our total volume, divided by our R constant, times the temperature. Again, we're going to check to make sure that our units cancel out. ATM, liter, Kelvin, leaving us with mole. And we get an answer of 0.16 moles. Remember, that is the total. So calculate the number of grams of each gas in the mixture. Well, since I know that CH4 has a mole fraction and that it would be moles of CH4 divided by the total moles, and I just solved for the total moles, I can just plug this in. So we would say 0.412, mole fraction doesn't have a unit because it's a fraction, equals our moles of CH4 divided by 0.16 moles. So that's 0.0659 moles of CH4. And because it asked me for grams, I can do my simple conversion. 1 mole is 16 grams of CH4. So that's 1.05 grams of CH4. And we can do the same thing for the oxygen. The mole fraction of oxygen is the moles of oxygen divided by the total moles. So 0.588 equals X over 0.16 moles. So 0.0941 moles of oxygen. And then remember that oxygen is a diatomic gas, so that's 32 grams of oxygen per 1 mole. And we get 3.01 grams of oxygen. A lot of times when you work an experiment, you're not collecting a gas straight out because that's hard to do. So you typically collect it over water. So what that means is you have your reaction taking place, there's a gas being formed, and it travels through the tube and through water, and then it's collected. But when that happens, some water is also changed into a gas. So when we collect it, it's actually in this case, oxygen gas and some of that water vapor. So anytime you collect over water, and that's what you got to look for, collecting over water, you have to take into account water vapor. So that's where Dalton's Law plays a role. At elevated temperatures, sodium chlorate decomposes to produce sodium chloride and oxygen gas. An impure sample of sodium chlorate was heated until the production of oxygen gas ceased or stopped. The oxygen gas collected over water occupied 57.2 milliliters at 22 degrees Celsius and 734 torr. Calculate the mass percent in the original sample. And then it tells you the vapor pressure for water at 22 degrees Celsius. The vapor pressure of water is temperature dependent, so they will always have to give you that information, or you would be able to look at that information on a table. Alright, so the pressure of oxygen is going to equal the total pressure minus the pressure of our water. So we would say 734 torr minus 19.8 torr, and that would give us 714 torr. Converted into ATM, and that is 0.939 ATM. So the moles of oxygen, we're just going to use our ideal gas law, or PIVNERT. Cancel out our units to make sure that we get the right answer, giving us moles. 0.0022 moles of oxygen. The question, though, is not really asking about oxygen, it's asking about sodium chlorate. So we're going to need to know the relationship between them, which means we need a balanced reaction. So it tells us that sodium chlorate decomposes to produce, so these are my products, sodium chloride and oxygen gas. 3 and 2, so we want to make them both 6. 2 sodiums and 2 chlorines, so we'll have to put a 2 there. And then it's stoichiometry. So based on our mole ratio, 3 moles of O2, 2 moles of NaClO3, and then use the molar mass to find grams because we want to know the mass percent. 106 grams, 0.16 grams of sodium chlorate. Alright, so that means 0.16 grams, that's our part, divided by the mass of the impure sample, times 100, gives us a percent of 18.